Good noon, everyone. Shall we begin? Am I audible? So, before begin this lecture, I guess many of you have observed that Moodle, the availability of Moodle is not really continuous, or at some time it might not be available. So, for this submission, the lab submission, what we'll do is for initial sum lab, we'll take the submission via Google form. The link for same is already shared in the chat. Right, and those who already submitted the first lab on a Moodle, I request them to resubmit them on the Google form too, so that there would be uniformity for all. Right, and one more thing. In a Google form, you are supposed to specify the email ID that you have used during this Google Meet registration. So make sure that you exactly use the same email ID. If you use some other email ID and the mapping will not be there at the back end, then it might possible that that particular lab will not be evaluated even if you have submitted that. And for a particular laboratory, after the deadline, I will publish the list of submission so that you can verify whether your submission is available at our end or not. Is it fine? And the deadline will be same, 18. After 18, I will just close the submission. So lateral, you cannot able to submit the assignment using the same Google link. Any doubt in this? And I hope you got the link too, the Google form link in the chat. And remember that in that Google form, the condition is set that you can submit your assignment only once. So even if it is incorrect assignment, then lateral you cannot able to modify it. So make sure that you submit it correctly. Fine. Now let's start the discussion. So far we have discussed different performance measures starting with the accuracy and up to the mean square error, MSE. Right. Now before that, the original classification algorithm, we need to cover one more thing, that is how can you evaluate the training performance. So for that, we are introducing three terms: overfitting, optimum, or you can say the perfect, and the third is the underfitting. Assume that these dots are actually our data points, and in all three graphs, this line indicates the function that we have learned. Once again, these are our data points. So assume that at x1 is a feature and x2 is our label y. Fine. So if I consider a particular data point, what you can consider the projection on x1 and on x2 for a particular data point. So whichever projection is on x1, that is a given value of x, and whichever projection is on x2, that is your predicted value of x2 with respect to a given x1. And so that is the meaning of individual data point. And this line in a second graph, this line indicates the function that you have learned. That also it indicates the error. Let's say the actual classification should be this red dot, but the line is classifying that particular x2 at somewhere else. Right? So that is a error for that particular point. Right? And similarly for all the point, we'll find the error and we'll sum that using some technique that we have referred in the previous lecture, like MSE. Fine. So in the second graph, if you observed, almost all points are covered by this line, but not all. Right. In the first graph, if you observe the first graph, all the points are covered by the given graph or given line. And in the third graph, we are just drawing a line where just 2 points are covered by that line while the other are not on the line. So the third is the example of underfitting, where your network is not properly able to provide the correct answer for a training data. Right? This is our training data, not the test data. Right? Second case, for majority of the training data, the network is able to generate the correct answer, but not for all. In the first case, overfitting, where for given training data, all the points are correctly classified by the learn function f. So which one from these three will consider as the best model? The optimum or the second model? Vivek is asking 18th midnight. Why why you wants to verify that whether it's on midnight or not? So can't we submit on 17th? So one answer is the first, and other are saying the second model is the best model. Why the second is best? It is misclassifying some example. Specifically, it is misclassifying the three examples. First cannot perform based on the test data. Yes, correct, Viral. New set at all. Yes. So basically, what happened? The model is overfitted. So it just know the thing which is available right now. So it just means that whichever data right now, that's it, that's the world. Right? So whenever some new data come, it may not able to correctly classify that new data. Why? Because you have overfitted that model with the training data. Fine. And in the case of second model, we are intentionally designing the model such that it will not overfit for a training data, so that the performance during the test would be better. And we'll see the technically how can we achieve this. But can you identify how can I know that whether a particular model is overfitted or not? Is there any way to identify whether my model is already overfitted or not? Cross validation, variance in bias, square error of training, huge gap between training and the testing loss. Accuracy in the training is more than in a uh, accuracy in a training is generally higher than the test set accuracy. But that gap, as Muktank is identifying, that gap must be larger. Let's say in a training you are getting 100% accuracy, while in a case of test, let's say you are just getting 50% accuracy. Or in general, if our model is reaching towards 100% accuracy during the train, there is a very high probability that our model is overfitted. Right? So in that term, yes, the training accuracy, if it is higher than the test accuracy with a very good margin, then we can say that it might be overfitted. So we'll see how can we avoid the issue of overfitting as well as the underfitting whenever we discuss particular algorithm, because that handling technique depends, or you can say it varies from algorithm to algorithm. But we must clear with the concept what is overfitting and what is the underfitting. Right. And one good example is given next to this graph. Let's say there is one quiz and the three students are appearing in that quiz. That, let's say, the student A, B, and C, where the first student, what C is doing, just guessing the answer and assume that it's a MCQ quiz. And with this, C is getting 50% accuracy. Student B know all the concepts which are discussed in the lecture, and thanks to that, he is getting 98%, you can say, accuracy, or 98% marks percentage. And student C is getting 92%, and her approach is the problem solving approach. So can you compare that A, B, and C with overfitting, optimum, and the underfitting model? Correct. All the answers are correct. Student A is an example of underfitting, B overfitting, and C, that is optimum. Right, and we should try to be student C. So in this, one more example of this overfitting and underfitting is discussed. So let's say that blue dots are the given points, and we have two model. First of all, let's say f of x, our function, is just the one single line. Let's say it's right now, if I consider this red line, the red line is our original function that we have learned, and this green line is the classification that we want to achieve. Now in the second scenario, whenever we are having theta 0 plus theta 1 x, that means theta 1 x1, that means we are having a linear relationship, or you can say the linear function, where depends on the value of this x, and this theta 1 and theta 0 are the parameter that we are supposed to learn. We'll get the line something like this. Third, let's say the cubic function, where we are improving the power of this x, which is our feature, till the cube, and the different combination of that. That is theta 0 plus theta 1 x1 plus theta 2 x1 square, and so on. And we will get the function something like this. And at the end, let's say, whenever we have the 90 degree function, we'll get the output something like this. So out of this 1, 2, 3, and 4, where m is equals to 0, m is equals to 1, m is equals to 3, and m is equals to 9, which function, or you can say which model, you will select for this prediction task? M is equal to 3, right? And I guess from this diagram itself, you might get some intuition how can we avoid the overfitting. Can I say that whenever m is equals to 9, that is an example of overfitting? So how can we reduce, or how can we avoid that overfitting? For this example, you can say by reducing the value of m, or you can say by reducing the degree of your function. In other term, can I say that by reducing number of features? Exactly, the Kashyap is discussing that, and also the Jainam. If we reduce the number of features, right now, what you can assume that over here in the cubic function, this x1 is one feature, x1 square, that is the another feature, and x1 cube, that is the third feature, right? And similarly, in this last example, there are 9 features. So if you reduce number of features, that is a one way to avoid the overfitting. And how will reduce a feature? We cannot just randomly reduce any of the feature. So for that, we need to follow strategy where we'll only reduce the feature which for which the impact is already covered. Or as Kashyap is explaining, we can reduce the unnecessary features. Yes, exactly, Vivek. The feature which are highly correlated. So when should we apply this thing? the feature reduction during the training, before training, or after training? Before training, pre-processing. During the training, we see those who are answering that during the training. So during the training, you cannot reduce the feature. During the training means, let's say you are training your model. Let's say we have the 100 examples. So for 3 examples, we are training the model on 100 features. Let's assume that we 100 cross 100 entry. And for remaining examples, we are training our model on 50 features. So that is something which is not feasible. So either you have to apply it before the training or the after the training, right? But the point is detecting the overfitting would be after the training. And actually this feature reduction is a process that you should apply before the training. Make sense? From this slide, we have concluded that if we reduce the number of feature, there is a chance that the overfitting will not be there. But for that, you have to at least detect that the overfitting is there. So when we'll detect that there is an overfitting? Once the training is completed, and if you try to check the training accuracy, then you come to know that no, this is the overfitting. Right. So once you detect that, you need to reduce the feature. But that feature reduction would be the pre-processing task. Make sense? Right. So the generally what people are doing in a pre-processing itself, they find the correlationship between all the features, and the features that are highly correlated, we can say that are highly similar. Almost similar impact would be there if I select one or the another one. From that set, from that highly correlated feature set, we'll just keep some or one feature and reducing the or removing the other features before the training. Then we'll train the model. And after training, if we still get this overfitting, then we'll have some other technique to reduce or to avoid this overfitting. Are we clear? What would be the flow? Yes, Akshay, correct. So let's say if we have two feature, length and height, or you can say length and width, then we can also create one new feature, that is area, and we'll remove length and width both the features. So that is once again one example of feature reduction. So there are many ways or many techniques to reduce the number of features. But we remember that we cannot randomly remove some features without checking its impact on the performance. It might be an important feature. And also there are some other technique like PCA, that is the part of our syllabus. So sir, we discussed that. So that are also the feature reduction technique. Regularization is also one another technique. So that we'll see once the syllabus progress, and that's why I told you that this overfitting, handling of overfitting, we'll see with different approach. But yes, this is the pre-processing that we can always apply independent to the data. If there is a correlation, we can reduce or we can remove a particular feature. Yes, Kata, we can use that PCA for the dimensionality reduction purpose. And in this week laboratory, we'll see this pre-processing task. where we'll reduce the feature by finding the correlationship between different features. If you just recall the last laboratory where we have discussed that the first and the second lab will be focused on the pre-processing task. So one of the pre-processing tasks that we will discuss in this laboratory is this feature reduction by this correlation finding, right? Okay, so with this discussion, let's start the first algorithm. Our first classification algorithm, that is decision tree classification. So far we have just we have started with the supervised learning. We have divided that supervised learning into two parts: the classification and the regression. Right? We have observed what are the difference between that classification and the regression. Then we have discussed different performance measure. Then we have discussed this overfitting, underfitting concept. And now let's focus on our first algorithm, that is decision tree classification. So the classification algorithm setting is something like this. Let's say we have a training data where we have different features, or you can say different parameter related to a customer. That parameter can be age, salary, profession, location, customer type, and so on. There can be many parameters, but let's just focus on this parameter. And we have our classifier, decision tree classifier algorithm, which performs some magic, and it will generate some rules, the decision rules. Where let's say the aim is we want to verify whether a particular person is eligible for the loan or not based on this parameter. So let's say this decision rule which is mentioned over here is, if a salary is higher than 5 lakh and the profession is executive, the person is executive, and so on. So by putting this and yes no kind of tree structure will decide or not. Fine. So let's say this example. Okay, we'll say we'll use two things. M means number of features and N means number of examples. So can you identify what will the value of M and N in this case? N is 10 and M 3, right? Correct. Where the fourth is our class label, that is Y. That is not one of the feature, right? And from this given data, our aim is to generate this kind of tree structure. And the interpretation of this tree structure is individual node represent a particular feature, where the topmost feature is the outlook. The next feature is the company, and the next feature is the board, the type of that sailboat, whether it is small or big, right? And based on the value of that particular feature will move towards the leaf of this particular tree, where the leaf indicates the class label. That is our last column. So the meaning or the interpretation of this is, let's say, after training, we are able to generate this particular tree, and assume that in a training we have used this 10 data. And now, whenever you have 11th entry, and assume that the outlook value of that 11th entry is sunny, will directly classify it as yes without looking at the other attributes, right? And let's say we have 12th example, and this example 11th and 12th are the test time example, right? Where the outlook is rainy. Then we'll check what is the value of this second feature, that is company, whether it is a big size company, medium size company, or let's say the no data for that. And assume that the company is a medium size company. Then we'll check the third parameter, the third value, the type of boat, whether it is small or the big. Based on that, we'll have the different answer, right? So this is a practice example for you. Can you identify the class label for this 1 and 2, that are the test data, using the same example, same decision tree? So when if you are saying that for both the cases, the answer is yes. So let's say for the first case, the outlook value is sunny. So outlook is sunny without checking other feature, we'll say yes. We'll classify it as a yes. For the second, outlook rainy. So we'll check the second feature, company. It's a big company. So it's a big company. The answer is yes. We'll not check the third feature. Fine. So if someone gives you this tree, the decision tree, can you easily classify the given data into one of the category? Or can you assign the class label to a given data, the test data? It's easy, right? But the point is, who will give us this decision tree? And that's what we learn in this chapter. Right? But be clear with the process. First, from the training data, we'll generate this decision tree. Then we'll also handle the overfitting by a technique referred as a pruning. And then for a given test data, using the generated decision tree, we'll assign a appropriate class label. So that will be the full process. Everyone clear with that? Right. So one more example. So let's say during the training, we have these 5 examples, and we'll decide some rules. The rules something like this. If the rank is the professor, or the years, the experience is greater than 6 years, then we'll say that particular faculty is the permanent faculty. So throughout this chapter, our focus is just to decide this rule or just to design the decision tree. And whenever we have the validation data, let's say these are the validation data, based on that we'll tune our classifier. And for a new, or you can say for the unseen data, we'll try to assign the particular class level. Recall that over here we have divided our data into three categories: training, validation, and the test data, or you can say the unseen data. Next, these are some common terms that we'll use with this decision tree algorithm. And from this all terms, many of these terms are already known to you since the third semester, right? Root node, the meaning is same. Leaf for the termination node. Branch, subtree, the parent child. The only important thing is this splitting. Means from a particular node, whenever we are dividing our data into more than one branch, or you can say more than one subnode. So what should be that node label? That is an important parameter, or that is an important thing that we'll learn in this algorithm. So that means if you just consider this first example, why I have just put this outlook at the root, not to the company, not to the sale board. So that's what we want to learn with the help of this classifier. And our aim is we will put a particular feature which can accurately or very nearly accurately able to divide the data. Right? And the decision node where we are dividing the data into the subnode. And this fifth point, pruning, that we'll use to avoid the overfitting, which means once we generate the decision tree, then we'll try to reduce or we'll try to remove some of the subnode or the sub branch from that decision tree. That method is referred as the pruning. And the reason is to avoid the overfitting. This thing will be more clear once we see the algorithm. In most of the decision tree algorithm that are available today, that are based on the top-down induction of the decision tree, and that are basically based on the Hunt's algorithm. And we'll construct it into the top-down manner. In our syllabus, we'll have these three algorithm: ID3, C4.5, and the card. The good thing for this decision tree classifier is whichever algorithm you choose, whether you choose ID3, C4.5, or cart algorithm, basically the approach is same. Only the splitting criteria or splitting parameter that we'll use, that would be the different. Means how you will choose a particular node, that would be the different. Otherwise, the full process would be the same. So to generate the decision tree, Some term that we'll use is the first thing is D, where D means our training data set, which includes the class label as well as the feature set. Right, so that would be the input to our decision tree algorithm. Next, attribute list means you can say the column head x1, x2, x3, x4, and so on. In the first graph, we have 3 attributes. And the next is the attribute selection method. So whichever decision tree algorithm will choose, that will have this thing, or you can say this attribute selection method as the different value or the different method for that. And what is the meaning of that? It's a process to determine the splitting criteria that divide your data into a subclass or the subsection. Right, and the algorithm will generate a decision tree for us. And so 3 input will there. One is our training data. The second and the D training data means all the X entry, that is all the feature set, and the Y, that is the class label. The second input to the algorithm is the attribute list. And the third is the method. We'll see which are different attribute selection method. Information gain, gain ratio, and the Gini index. See, there are many new terms for you. So if you cannot able to understand a particular terminology, then it might possible that you might be clear with the example, because this is the easiest algorithm, and whenever it comes to the calculation or the example, I guess everybody will able to do that. But let's say in a real world, whenever there is a need to apply the decision tree, it is very important to be clear with the process, the full process, because in most probably in the next lecture we'll focus on this information gain, that is one of the attribute selection method, right? And after the next lecture, that means in the next week, whenever we start discussing the algorithm, it might possible that you will just lost that what is actually the attribute selection method, what should be the use of that. And why we have this many attribute selection method is it will decide whether the division would be the binary division or the multiple class or the multiple entities would be there. So let's just try to understand this thing. Let's say for the training data set, we have 3 attributes, or you can say 3 features. In this decision tree algorithm, we'll refer it as an attribute, but later whenever we see the other algorithm like the linear regression or the logistic regression, we'll refer it as a feature. Ultimately, whether I will use attribute or the feature, remember that it's an column header, x1, x2, x3. The class means the y. This we are repeating since the first lecture. Right. So right now we have 3 feature. Let's say the one is the whether a particular person owns a car or not. Second is what is the type of that car. And third is let's say the ID. We can say the Aadhaar number of that particular person. Right. And assume that we want to classify our data into 2 classes, that is class 0 and class 1, and total 20 entries we have, where 10 entries belongs to the class 0 and the remaining 10 belongs to the class 1. Equal partition of data is there. So what will be the size of your input, or you can say what will be the size of your D? From this given intuition, can you say what will be the metric size for D? 20 cross 20 cross 2. No. Yes, 20 cross 4. Maliha, why 4? Exactly. 3 attribute and 1 class. Remember that in the D, we are also considering the class label. Right? So what we are assuming, we have 20 records. Out of the 20, 10 belongs to the class 0 and the remaining 10 belongs to the class 1. We have 3 features, on car type, and the ID. And the fourth column indicates the class label, whether it's 0 or 1. Right. Now, let's assume out of these 3, I will just choose the 1. I am designing the decision tree where there is only one node, that is a root node. And as in root node, I want any one of these 3 feature. So let's say if I select the first feature, that is on car, as in root node, and assume that wherever this on car value is yes, total 10 times that value is yes. Out of that 10 times, 6 times the class label is 0, and remaining 4 times the class label is 1. So that are the 10 entry. The remaining 10 entry, that is on car, will have the answer no. And out of that 10 entry, 4 times the class label is 0 and the 6 times the class label is 1. So for the on car, we have 2 values, either yes or no. For the car type, we have 3 values. Either it can be a family car, sports car, or the luxury car. So if it is a family car, total, how many times the family car is there? During the training process, how many times we have observed the family car? 4 times, right? Out of that 4 times, how many times the class label is 0? Once. And the remaining 3 times the class label is 1. Similarly, for the sports car, we have observed that sports car 8 times, and for all 8 times the class label is 0. For all that 8 example, the class label is 0. Luxury car, 8 entry, 1 entry with the 0, 7 entry with the 1. And for the ID, how many different values we have? We are assuming the Aadhaar ID. So everybody will have the unique Aadhaar number, right? So all 20 will have different Aadhaar numbers. So let's say that numbers are C1, C2, C3 up to C20. And every subtype will have either class level 0 or the class level 1. So are we clear with this diagram? Everyone? And the attribute selection method that we'll choose is that will decide out of this 1, 2, and 3, which one is the best attribute that we can choose right now. So from the given data, can you identify which one is the best attribute? Okay, car type. So we have 20 records and assume that this particular car type feature will have three different value. Either it's a family car, sports car, or the luxury car. Right. If it is a family car, there are four examples. This 3 plus 1. There are four examples where the car type is the family car. Out of that four, one example will have class level 0 and remaining three will have class level 1. And if we just quickly recap the sport, there are 8 entries with the sport car where all 8 belongs to the class level 0. Okay, Akshay. So the best condition, I guess everybody agree with that. ID is not the best splitting criteria that we should choose. Some of you are saying that own car is a good splitting criteria, and some other are saying that the car type is the good splitting criteria. So those who are saying that own car, specify that OC and the reason, and those who are specifying car type, specify city and the reason why you feel that the car type is a good criteria, or why you feel that the own car is a good criteria. Also the reason, Vyom. Exactly, both the answers are correct. Vyom and the Ghata. So the aim at the decision tree algorithm is whenever you split your data or whenever you select a particular feature, what we want that after splitting the data, that is, let's say if I select this car type, so at the next level, we need a particular cell to be fully pure or as much pure as possible. I can say this sport is a fully pure class level. Why? Because all there are 8 entry in the sports and all 8 belongs to the class 0. Over here also, we can say it is almost pure where 3 belongs to the, so that is 75% pure where 3 belongs to the C1 and the remaining 1 belongs to the C2. And same thing for this luxury. But if I consider this own car example, C0 and C1, 6446. So that is not the proper distribution between the class. Right? So always our aim is to choose a feature such that we can maximize the examples in a particular class which all belongs to the same category. Is it fine? So right now from this example, we have identified that, but one of the attribute selection method that we'll discuss that will automatically identify which out of these three is the best feature to be selected. And in this full algorithm, what we will do is using attribute selection method, we'll select our attribute, we'll divide the data. For example, let's say now we all clear that in this example, I will select this car type as an attribute. So I will divide the data something like this, the family, sports, and the luxury. And now for this leaf level, once again, I apply this attribute selection method, and now I will choose the next feature for the division, and so on. And likewise, we'll generate this decision tree. Does it make sense? Okay, so before discussing the next slide, when can we say that it's a pure distribution and when can we say that it's a totally impure distribution? The worst scenario and the best scenario. In terms of probability, let's assume the binary classification. When can you say that it's an pure distribution? Zero in C0, that means one in C1, right? If we consider the so 50-50 both means it's a pure or it's so over here in this case it's 50-50 scenario. Own car. Almost 50-50. Not exactly, but almost 50-50. Once probability is high. So what is the maximum value for the probability? 1. So can I say that let's say class 0 and class 1. So class 0 probability is 0 and the class 1 probability 1. That means the pure set as well as the reverse. That is class 0 probability 1 and class 1 probability 0. Once again the pure set. And impure class 0 is equals to class 1 is equals to 0.5 probability. That you can say the highest level of impurity. And these are the measure, that is the entropy, Gini value, and the classification error that will use to measure the impurity whenever you divide the data using a particular feature. Fine. So next lecture will start with the first example, that is information gain.
Okay, good afternoon, all. Uh, Today, before we start, we will today. What is our agenda? Our agenda is to learn about arithmetic operations on image. Then we will go for image negative, power law transformation, log transformation, etc. So for that you will need some images. So before we start, to log into your Moodle, download the images that are given to you. One folder is practice images, another folder is chapter 3 images. So please all of you download that. Okay. So that along with me you can also try. So once you complete the downloading, just let me know so that we can move further. I'm waiting till time that you will be able to download your images. Chapter 3 images from Moodle and practice images are placed on Moodle. Check your Moodle, download it and acknowledge. Are you following me? I think, okay, are you clear with what you have to do? Are you clear with what you have to do? Okay, please download the images. Okay, those who are not having Moodle access, I need to put that on that Google Drive. Wait, I am putting it on Google Drive.